So we all know a culture, do we know a culture? Bacteria culture. So we start with 500 bacteria and it doubles in size every half hour. So it's going to grow in an exponential sense, and we are going to model it as an exponential model. So what is the general form of an exponential model?
Y equals A, B, C, X.
F, A, B, C raised to X. So, or either with red. So I'm just going to rewrite this as the amount of bacteria at time t, A all t, which is equal to A naught, and E raised C times X. I'll just call it K times T, or R times T. If you want to use the paired version, you can. It's entirely up to you. I just wanted to show all possible ways to write an exponential function. So what is A sub 0? 500. It is the initial value. So we would end up having 500 multiplied by E raised kt, because the initial value is 500. What are we missing in order for us to proceed forward with the other parts, B, C, D? Rate. So the rate here is K, and bacteria is growing, and we know that it doubles in size every half hour, which means it is growing. So K has to be positive. If K is positive, it's growth. If K is negative, it's decay. So how do we find E raised kt? Well, doubles would simply mean what value? So at some time 2000, excuse me, at some time t, it is equal to E raised k multiplied by t. So k is k and half hour, so 1/2. Double the initial value. So 500 initially, now it became 1000. What time? You started time 0 and time 1/2 in hours. So 500 there, 1000 there. Good. Now, if you divide, you end up getting E equals E raised k multiplied by 1/2. Good. So that is a natural, that uses a natural base, which is E 2.7182, so E raised k multiplied by 1/2. But solving this requires the knowledge of natural logarithms, and having gone over natural logarithms. So what do we do? Cancel out the E. We can't cancel out the E yet because I haven't, talked about natural logarithms. What do we do? Abandon ship. No log yet. We want to do this without logs. Done it. Good. So remember last time I mentioned that B could be any number, right? It could be any base that you want. You could have it as 10, you could have it as 5, you could have it as 2. E is the mathematical case, it's natural. So what if, instead of picking B to be E, I pick B equals 2, right? So I'm going to get rid of the E. So I simply have 2 equals 2 raised K multiplied by 1/2. Correct. With me? How do we solve that? Algebra 101. Well, let's see if it comes back to you. I'll put a 1 there. Set it equal to each other because it's just 2. So I can write that as 1 equals K times 1/2. Therefore, K is equal to 2. Does that make sense? Yeah. So it felt like, oh, I got stuck here. I got stuck at this point because I haven't gone over natural logarithms, but it is coming back to you for a sum. So the proper way we're going to use natural logarithms and get the answer easily. Since I haven't gone over that topic yet, I'm using 2 instead of E so that I can directly equate them together. Does that make sense? So the rate K is now 2. So what would our model be? Can I put this on? The initial value is 500. Should I put 2 or E? 2, because I changed that E to a 2. So I have 2 raised to 2. So if you plug in T equals 0, you get 500. If you plug in T equals 1, you'll get 4,000 and so forth. If you plug in half, you will get 1,000, etc. So how many are we clear with this? So this is our model, and we are going to use this to answer the other parts. This is a growth model, so it better keep on going. So we have answered part B of that. Do you agree? At some arbitrary time. So this is the answer to part B. I will start this way, but the book is doing it a different way. So part A, how many bacteria are there after 3 hours? How do we find this? Set T equals to 3. So if T is 3, you have 2 raised 2 times 3, which is 2 raised 6. And that is 64, which is 10 to 2, 3, 2, 0, 0, 0, 32,000.
So the 6 is in the parentheses this time?
It doesn't matter, right?
Oh, okay.
Because, I'm just doing 1 times. If it's confusing you, I'll put it this way.
No, just want to make sure.
Good. So at the 3-hour mark, it will be 32,000. In a problem, part C. It's one thing to know the number of bacteria at 40 minutes. Well, I know the amount at half an hour. Let's just compute what happens at exactly 1 hour. How do we do that? We simply plug in T equals 1. If T is 1, we would have 2 squared times 500. We'll get 2,000. Yes. So that is 2,000. problem wants to know how many bacteria are there after 40 minutes, in other words, at 40 minutes. Process of elimination, whether you're doing SAT, MCAT, LSAT, whatever. It's 1,000 here, it's 2,000 there. So your answer has to lie between 1,000 and 2,000. Anything else cannot be an answer. So how do we plug in 40 minutes?
Turn in the fraction of an hour.
Turn into the fraction of an hour. An hour has 60 minutes. So 60 times x must be equal to 40, right? And we need to find that x. So x would be 40 over 60, which would be 2 over 3. So 0.667. Does that make sense? The put 60 times some portion gives us 40 minutes. 40 minutes. So what hour would be? That would be 0.667 of an hour. Does that make sense? So you have to have the same units, which is why I converted hours to minutes, because I'm comparing it to minutes. So now we take t equals 0.667. Let's see if that answer falls between 1,000 and 2,000. If not, my entire life would be wrong. Okay, what do we get?
1,059.92 something. It's 12,059.92.
12,000?
I mean 1,200, sorry.
Okay. 1259.92.
92.
92, so approximately 1,262. Does that make sense? And it certainly lies between 1,000 and 2,000. Good. It is an exponential model, so it's going to grow rapidly after a certain point.
Yeah.
So we need to find, the problem wants to know, or the problem wants to see a graph of this curve. So we are going to write our function, which is 500, to, within parentheses, raise to x. Good. If you graph this, we're not getting a good picture, right? Because it's going to cross the axis at 500. So we've got to adjust the window. The smallest value of x can be 0 or should be 0 because we can't have negative time. So t starts at 0, so I'm going to set the value of x to be 0. The maximum time, should we go all the way up to 5? We did 3, so let's go up to 4. That will be large too. We'll stop at 3. And the minimum value, I'm going to start at 500, go all the way up to, let's say, 40,000. I want to change the scale, right? If the scale is in measures of 1, we're saying I walk along the x-axis from 500 to 501, 501 to 502. That is a lot of steps to take between 500 and 40,000. So I just want to, hop. So I'll just put 2,000. That might work. The graph. Good. So you've got to be cautious here. This value is not 0. it's 500. I've adjusted the window. So I start at 500 and I'm going this way. It tells us this value right here is 2,000, 8,000, and that. Good. The same part D, wants to know the time at which it becomes 100,000, right? You could do this using the table function. So we know at 3 it becomes 32,000. So our answer has to be bigger than 3. So I'm going to arbitrarily start at 5. I get 512,000, exceeded the 100,000 mark. So So 2, 3, 4, 5. Here we exceeded 100,000, 512,000 bacteria. So let's try 4. 128,000. So at 3 it is 32,000. And at 4 is 128,000. So our answer for 100,000 has to be between 3 and 4. Do you really want to try each and every number? No, there has to be a better way. So the last part, we want to estimate the time for it to reach 100,000. Going to, well, just erase right here. For some time, or at some time, it becomes 100,000. That would equal to 500. 2 raised t multiplied by 2. That is our rate. Correct. So 100,000 divided by 500, those 2 would go away, and 50 will have 20. 20 would equal to 2 raised to 2. Good. So we want to still find the value of t. Is it possible directly to do this somehow? How?
You just set fairly soon, or you just set y equal to that, and it's all.
But how?
Erase the initial parentheses instead of the extreme with us.
Huh?
We make 20 a base of 2 and then.
Right, we want to make 20 a power of 2. Well, how do we make 20 a power of 2?
2 to the power of something.
Huh?
2 to the power of whatever.
2 to the power of something. So let's say 20, 2 to the power of something, 2 raised 4, that's 16, right? How about 2 raised 4.5? That's a bit bigger one. 22, still exceeding that value. How about 2 raised 2.5? Well, with the parentheses. 5.6. Not bad. Have to exceed 4. 2 raise 4.125. 17. 2 raise 4.2. 18. 2 raise.
This is the only way to do it?
There is an easier way.
Wait, what exactly are we trying to do here?
19. I want to get to 20. 4.3 is about 19.698. So I'm going to do 2 raise. Did you say 4.37?
Also, sir, I found out the time in which it becomes 100,000.
How?
Oh, no, I was just doing it by hand.
Oh, we're doing the same thing. Let's just do approximately 4.3. So 2 raised 4.3 is approximately equal to 20. So now I can directly equate them together. So 4.3 would be equal to 2t, which would imply t is equal to 4.3 divided by 2. 2.15. That can't be right.
It's 3 points. Let's see. It's 3.82193.
Why is it I making a mistake here? 100,000 equals 500. The rate is 2t. So 2 raised 2t is equal to 20. Yes. 2 raised 4.3 would equal to 20. 4.3 over 2. It's 2.15. That's weird.
Would it be 200 instead of 20?
Yeah, that's one.
Mhm.
10. And that would make it 10,000, right?
No,
Pretty sure it's 200.
Do they think 100,000 is?
No, it would be 200.
Sometimes simplification may not be a good idea. So I should have divided it by 5. I divided it by 50. My bad. So it's 200. You see how I corrected myself? So I've got to change that power now. So 2 raised 6 is 64. 2 raised 7 is 128. 2 raised 8 is 256. So this has to be between 7 and 8. Because we want 200. Let's do 2.73. 157, 2 raised 7.8.
2.76, no, 7.64,
7.64, okay, that sounds much better.
7.64.
So 7.64 over 10, so the time is 3.82. And now I can sleep at night. Because everything works. So 2 raised 7.64 will give us that value. So you can see how difficult this turned out to be. There has to be an easy way. And that would be the next section. Now, sure, we could even do the exact same problem, but a start, and we will start with this example so you understand as to why logarithms are important. Are we clear? Okay. So the rate cannot be 1.5 because it becomes half of what you had initially. So the initial amount is A naught. Do we agree? And I'm going to use the power of 2. I think that will work nicely in this problem. If not, we could always change that power. Once again, I'm doing it this way because we haven't gotten into logarithms. In the homework, started after I do logarithms, it will be easy. And so there are a couple of ways to do this. Half-life simply means it goes to half of the original amount that you have. You can either use this number that they have provided, right? At midnight, if you start at 0.6, what would it be after 1.5 hours later? The half-life, 0.3. Do we know what half-life is? Right. Anytime, any medication that you take, it has a half-life period, the amount that it decays in your bloodstream. Some have a really, really long half-life, 4 days, 6 days, some goes away rapidly. So either you can make use of this information and then solve for K, or do it in a very generic way. I don't care about what that initial value is. At time t equals 1.5 hours, which is simply 3/2. That original amount becomes half of what it was. Yes, so I'll simply do A0/2 is equal to A0. Good. And that would equal to 2 raised k multiplied by 3/2. This is the same as saying I will start at 0.6. 1.5 hours later, it becomes 0.3. Correct? Over here, you would divide 0.3 by 0.6. And you have 1/2 is equal to 2 raised 3/2. Good. The generic version cancel out the A0. You would have 1/2 is equal to 2 raised 3k over 2. This and that are one and the same. Do you agree? But which is better? That. Why? Can someone tell me?
Oh, sorry, we're talking about between which versions?
Yeah, and I'm going to tell you that this is better.
Oh. I was just writing everything down.
But why?
So you're saying between the two versions of the question overall, that one would be better.
This one would be better.
No, I was saying, you're saying between the two versions of the question.
Between these two versions, do we agree both are ways to solve for k? Yes. Between these two versions, I'm going to ask you which is better, which is more effective.
The one on the left, because it can be applied to multiple.
One on the left, my left or your left?
Because
My
you-
left. This is my right hand.
Oh, sorry, all right, you're right hand, I'm sorry, all right.
It's okay.
I missed it very well.
So one, my right, your left.
Yes,
So
it can be applied to multiple lines.
exactly. So if you start it this way, it can be applied to multiple models. In other words, if someone says 1/8 of the original amount, you change that to be A0 over 8. 1/10 of the original amount, you could do it as A0 over 10. Not only that, if you encounter a problem where that entire line is not given to you, right? Then the only way to solve is using this. Do you agree? I did this without using the 0.6. So if that last statement is not given to you, this is the only way you can do it, which is why I recommend this. Good. It's very generic. Okay. I wrote it in power of 2, that's for convenience. That 1/2 would simply be 2 raised negative 1. 2 raised negative 1 would equal to 2 raised 3k over 2. Yep. The bases are equal, so we can simply use algebra. Negative 1 would equal to 3k over 2. Multiply by 2 on both sides, negative 2 would be equal to 3k, which would imply k is equal to negative 2 over 3. We can leave it as is, or you can write it as 0.667 with a negative. Are we set? Okay. So I found my model. So A of t is equal to 2 raised negative 0.6667 multiplied by t. And clearly the rate is negative, indicating a decay moment. Good. So everything worked out. Now, I want you to graph, and they say use the graph to determine when your BAC is 0.08 milligrams per milliliter. We're using a graph once again. Last time we used the table, right? We guessed a bunch of values. Here, I'm going to use the graph, which means what function should you use on your calculator?
It would just be the y equals the variance graph.
But last time, do you follow my question? Last time we used the table, put in a bunch of values, and or use the calculator manually.
Oh, you're talking about using the trace function.
Trace function, yes. If you use the trace function on the calculator, you should be able to get the time when you have 0.08 milligrams per milliliter. I'll give you a few minutes and let's see if you can graph this and use the trace function to give me an estimated value for the time when your blood level is going to be 0.08. Now do keep in mind, we want to know the initial time. What is the initial time? T equals 0.
That's why we midnight.
Midnight. Go ahead.
Just asking, check this real quick, yeah, since they don't- Wait, were we recording that entire time or are we recording now?
I'm just recording now.
Oh, okay, beautiful.
It's okay if people hear it. I'm not saying anything inappropriate, it's the truth.
No, no,
So we have 2 raised negative 0.6667 t. We want to find the time when we hit 0.08 milligrams per milliliter. How do we go about doing this? If we want to take the approach that we did last time, we raise this to the power of 2, don't forget the negative sign, or you can simply use the power of 2 and keep equating different values. Here, the book wants to use the graph, so I'm just going to use the graph. We start at an initial value of 0.6. Yes, that's where we start at midnight. And multiply by 2. Raise we need to 0.6667 x. Graph. We see nothing.
I think
Like
I have to
this.
change
The
the.
window, right? So window is very, very important in calculus because if you know how to adjust this, you can get the correct answer just by using the calculator. So the minimum, yes,
Isn't it 0.667?
Isn't it?
667.
it's 0.6667, don't worry the thing.
Oh, right.
It's just that, yeah. You know, you can approximate it to 0.67. Okay, so I'm going to adjust the window. I know the maximum value, we're starting at 0.6, so. Point six, time cannot be negative, so I'll put 6 hours and see what happens, and. So the maximum value is 0.6, minimum is 0, if we want to get to 0. Now, the scale will tell you how accurate you can get the answer, right? How close you can get to the answer. I'm going to set it at 0.02. Good. Right. Good. Trace. 3 hours, I have 0.149. Slowly moving closer and closer. Right there,
Hey, that's pretty
4
close.
points, what, it's very close, 4.34 hours. Does that make sense? So if you had 3 standard rings, and if your all-core level was 0.6, at the beginning at midnight, it is going to take 4.34 hours for it to reach 0.08. Does that make sense? And keep in mind, this article that's referenced in the textbook did this in the fasting state, but this will change, this model will change depending on multiple factors, age, gender,
Body weight.
underlying conditions, body weight, height, etc., etc., etc. So don't take it for granted.